All right, almost in the home stretch with geometry. So we've got AY4, AX4, AX5, and AX6 coming next. So let's do the AX4s. Now, for the AX4s, we have possibility of doing an AY4, an AY5, and an AY6. So if we have AY4 and we have 4 periphery atoms, this means that we have an AX4E0. And means in this case, the electronic and molecular geometries are the same. In this case, this is going to be tetrahedral for both. So how does it get more complicated? Well, let's say we have an AY5. If we have 4 periphery atoms, this puts us at AX4E0. Now the complication with this is that once we start getting to these AY5 and AY6 electronic geometries, we have axial and equatorial atoms. And where things go depend on the size of the periphery atoms. So let's say we have something small like hydrogen or fluorine. Well, what's going to happen is the lone pair is going to want to occupy the prime sites. And the prime sites for something that is trigonal bipyramidal electronically are the equatorial positions. So if we have small periphery atoms, in this case hydrogen and fluorine, we're going to end up with a sawhorse or seesaw molecular geometry. The lone pair is going to want to go off here because they are as far away from the other atoms as possible. But let's say we have large periphery atoms, something like bromine or iodine. Well, for large X, we're going to force the lone pairs to go into the axial position, and this will give us a triangular pyramidal geometry. So in the case that we have large periphery atoms, again, something like acetine, bromine, iodine, a really fat halogen, what they'll do is they'll force the lone pairs into the downward position, the axial position, because it puts the lone pairs at 90 degrees to everything else, but it maximizes the distances between the periphery atoms. Now the last one, AY6. If we have 4 periphery atoms, we'll have AX4E2. And again, we have to decide where we're going to stick the lone pairs. If we have small periphery atoms, something like hydrogen or fluorine, we want to maximize the distances between the lone pairs, and the best way to do this is to put them in the axial positions. And so what we end up with are 4 periphery atoms all in the same plane with the central atom, and this is a square planar molecular geometry. Now, in the event that our periphery atoms are large, something like bromine or acetine, this will force the lone pairs to go into the equatorial positions, and once again we will recover a sawhorse, large periphery atoms, sawhorse or seesaw configuration. Now, something like this you're not going to really see with the atoms we deal with in Chemistry 151. This is typically, when we see the sawhorse configuration with an AY6, we're looking more at transition metal complexes, and it's a lot more complicated what's going on. But these are your molecular geometries that you can possibly get if you have 4 periphery atoms, depending on the number of lone pairs in the central atom.